The purpose of this video is to do some work on molecular drawings and looking at the idea of polyatomic ions and how I need to consider the idea of the extra electrons or lost electrons in doing my drawings. We're going to try to touch on coordinate covalent bonding and resonance structures. If I run out of time on my little 10-minute time limit, I'll do a second video that will show resonance structures. NH4 plus, we can see that there's a plus sign here, which means we have one electron lost. So when we go to draw this, we realize that nitrogen has 5 valence electrons, so that's going to go in the middle of my drawing. And I'm going to take my hydrogens, and I'm going to start over here at the west or the left, and I'm going to start to spread my hydrogens around. I circle up, circle, 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 and I start matching up, match up, match up. And if it was NH3, I'd be done, but it's NH4 plus, so I need to add in that hydrogen. When I look and I think at this moment about this one electron lost, I look at hydrogen, which has an electronegativity of 2.1, and nitrogen with an electronegativity of 3.0. So my tendency is to say, well, this hydrogen is going to lose this electron, and it's actually technically coming in as H plus. So I'm down 1 electron total, and I see then that I have this lone pair of electrons, and what I want to envision is this hydrogen coming in and sitting in on this lone pair of electrons. That's called a coordinate covalent bond. A coordinate covalent bond is when the electrons are donated by one atom. So it's a covalent bond, but nitrogen is contributing both of those electrons. If I draw this as a Lewis dot diagram first, and I show nitrogen's electrons there in blue, and now I bring in my hydrogen, and my hydrogen, and my hydrogen, I can see that I'm meeting the rule of 8 all around, and I can see that each hydrogen is making the bond that it needs to make, but I can identify my coordinate covalent bond in comparison to my regular single covalent bonds. The truth, though, is when I go to draw this Lewis structure, it's just 4 single bonds. And chemically speaking, there is no difference between the coordinate covalent bond and the regular single covalent bond. Coordinate covalent bonding is just a way for us to try to explain behavior that is observed. Ammonium is clearly an ion that exists. If I want to add into this a little bit, I also should consider and look and think about my structure, and I can see that I have 4 single bonds there. I can see that I would indicate this as tetrahedral for its electron pair geometry and tetrahedral for its molecular shape, and I would have bond angles of 109.5. A second example would be SO4 2-. We know that SO4 2- exists, and when we look at SO4 2-, we think about the sulfur as being the central atom, and we're going to spread the oxygens around. The oxygens are really basically attackers. They have an electronegativity of 3.5, and they are pretty much like fluorine. They're pretty much going to take care of their electron needs, if you will. So we're going to spread these oxygens around. Okay, and then we're going to take a look, and we're going to see that we've got this 2-. This 2- means that we have 2 electrons that have been added in. We've gained 2 electrons. I'm going to put one of those electrons over here on the left side and another electron down at the bottom. And what that does is it lets me actually see that I can singly bond these 2 oxygens to the sulfur, and they are now meeting the rule of 8. They're making a single bond, but they have that extra electron, so they look like they have 8 electrons each. I then sort of now work my way around counterclockwise, and I see that I've got these 2 other oxygens that still have 2 bonds that they want to make, but I've got sulfur with its lone pairs sitting there, and I generally am not thinking about those sulfur as bonding with those lone pairs. We're going to do here coordinate covalent bonding again. At this level of learning, we do a coordinate covalent bond. You can go out onto the internet and find some support for some double bonding, but We're going to use coordinate covalent bonding to get out of this structure. We're going to say that this is paired up. We're going to say that this oxygen sits in. We're going to say that this is paired up. We're going to say that this oxygen sits in. So what I can see is that I've got sulfur, and my sulfur is making 4 single bonds. If I want to do the same thing and show ownership of electrons, I'm going to show sulfur with its 6 valence electrons, and I'm going to show each oxygen coming in on those valence electrons. And my oxygen at the left or the west and my oxygen down at the bottom or at the south each have 6 electrons, and they pick up an extra electron. They pick up an extra electron, each of those. And then my 2 other oxygens have their 3 lone pairs spread around. Chemically speaking, just like we saw with the NH4 plus, chemically speaking, those bonds are identical. So what we really see is sulfur making 4 single bonds. I've got my 4 oxygens. I've got my 4 oxygens all with 3 lone pairs. 3 lone pairs, 3 lone pairs on all of them. Make sure you're showing all of your lone pairs. Brackets and a 2- charge. And again, I can see that I've got that tetrahedral structure, XAAA, and I would say that it's tetrahedral for electron pair geometry, and tetrahedral for molecular geometry, and 109.5 for the bond angle.